and one of them is particularly notable. Titan is the second largest moon in the solar system, and it possesses an atmosphere remarkably like Earth's. It is primarily composed of water ice and rocky material. It is even possible that under the clouds and surface ice, Titan has liquid water and maybe even microbial life. It is 50% larger in diameter than our own moon and 80% more massive. Saturn takes 29 years to orbit the Sun, and does so at a distance of 890 million miles. Uranus rolls on its side. It is an icy giant of a planet, the third largest in the system. Like the other giants, Uranus has a ring system and numerous moons. It is the seventh planet out, and it orbits the Sun at a distance of 1.9 billion miles. A year on Uranus lasts 84 Earth years. Because of its extreme axial tilt, seasons on Uranus are worth a look. At the time near the solstice, one pole continually faces the Sun, while the other faces away. Only a narrow strip near the equator experiences Uranus' 17-hour day. At the other side of Uranus' orbit, the orientation of the poles is reversed, so each pole gets 42 years of continuous day, followed by a 42-year night. Okay, let's head to a point high over the ecliptic, so we can see the relative sizes of the orbits of the sunward planets. Neptune is a blue world. It is the smallest of the giant planets in our system, but still 30,000 miles in diameter. Since the demotion of Pluto, it is the furthest planet from the Sun. Neptune's rings are very faint, and of its 13 moons, only Triton is massive enough to be round. It rotates every 16 hours and orbits the Sun every 165 years at a distance of 2.8 billion miles. Pluto is now deemed a dwarf planet and a member of the Kuiper Belt. The Kuiper Belt is a region of the solar system that extends just beyond the orbit of Neptune, at about 2.8 billion miles out to about 5 billion miles. Like the asteroid belt, it is crammed with many small bodies orbiting the Sun, most of which are frozen methane, ammonia, and water. Here's a size comparison. Earth, Ganymede, Titan, our moon, and several bodies from the Kuiper Belt. Currently, the largest known Kuiper Belt bodies are Eris, Pluto, Sedna, and many more without formal names like FY9 and EL61. We know mass distorts space. We know light is affected by gravity. And we know Einstein's theory of general relativity makes possible one of the strangest objects ever imagined by physicists. If you could create a large enough distortion in space-time, by placing enough mass in a small enough space, you could create a region of space-time so strongly curved that nothing, not even light, could escape it. And since nothing can travel faster than the speed of light, anything that entered this region of space-time would be trapped there until quantum mechanical effects allowed it to escape. Black holes can come in any size and have any mass. All that is required is that enough mass can be concentrated to the point where it collapses under its own gravity. Stellar mass black holes are formed when stars 20 or more times the size of our own Sun finally run out of fuel in their cores. They rapidly cool and collapse, and the shockwave from the collapse blows the outer layers of the stars to bits in a colossal explosion called a supernova. But the small, dense core of the star can remain bound together by the force of gravity. As it continues to collapse inward under its own weight, the atomic particles of the core are smashed together until all that is left is a black hole. In its center lies the singularity, the mass of an entire star crushed into a single point in space. Surrounding that is an invisible shell called the event horizon. This is the cosmic point of no return. Once inside the event horizon, nothing, not even light, can escape except through quantum mechanical processes. Supermassive black holes may contain billions of times the mass of our Sun. These monsters lie at the center of every large galaxy. Micro-black holes have tiny masses at which the effects of quantum mechanics are very important. Black holes of this type have been proposed to have formed during the Big Bang and would quickly evaporate due to said quantum mechanical effects. At the end of their life, it is believed that they would emit a sudden burst of energetic particles, but no such bursts have been detected as of 2008. We can never see into or directly know about what happens inside the event horizon of a black hole. In effect, any object that crosses this imaginary line has left our universe for good. But if nothing, not even light, can escape a black hole, then how do astronomers manage to detect them? It is possible to imagine spotting a solitary black hole by observing the bent starlight from behind it. But a better chance of detecting one would arise if they were not alone in space, but accompanied by another star. This black hole is drawing matter from a companion star, which orbits it at a distance safely outside the event horizon. As the gas spirals into the black hole, it heats up and emits huge quantities of high-energy radiation. Intense radiation emerging from a small area, or stars orbiting small invisible companions, these are telltale calling cards of a black hole. $12.5 billion years ago, the universe was littered with the remains of first-generation stars, and billions of second-generation stars were born from these clouds. Small groups of these new stars were drawn to each other gravitationally and merged to form ever larger and larger groups. Our own galaxy, the Milky Way, is an example of a spiral galaxy born in this early era. Today, it contains about 200 billion stars and is still growing as it absorbs small neighboring clusters of stars. The center of our galaxy is in the direction of the constellation Sagittarius.